Hello everyone. In this lecture we will do some practice questions based on geometric series. Before starting with geometric series, we must know what is series. Given a sequence an of real numbers, summation n running from 1 to infinity is equals to a1 plus a2 plus a3 plus so on to an plus so on to is called an infinite series. Here an is the nth term of the series. So series here is nothing but adding all the term of the sequence. Now what is sequence of partial sums? Let an be sequence of real numbers, then Sn is equals to a1 plus a2 plus a3 plus so on to an, then the sequence Sn is equals to S1, S2, S3, so on to Sk and so on to is called sequence of partial sums. Partial sum. Here we need to note here is that S1 is nothing but the first term of the sequence an, and S2 is the sum of first two terms. Similarly, S3 is the sum of first three terms. Similarly, this is sum of first k terms of the sequence an. So this sequence is known as sequence of partial sums. There is some result that let summation an be series of real number, then series converges, diverges, or oscillates if and only if its sequence of partial sum does so. So what does this means is that series an will behave the same way its sequence of partial sums does so. If sequence of partial sum is convergent, then series is convergent. If sequence of partial sum is divergent, then series is divergent. If sequence of partial sums oscillates, then series also oscillates. Now the next definition is geometric series. Series of the form A plus A into R plus A into R square plus so on to A into R to the power n minus 1 plus so on is equals to summation A into R to the power n minus 1, where n is running from 1 to infinity, in which A and R are fixed real numbers and A cannot be 0. Note that here the value of R can be positive as well as negative, and if the value of R is equals to 1, then nth partial sum of geometric series is Sn is equals to A plus A into 1, because value of R is 1, A into 1 square, so on to A into 1 to the power n minus 1. This is nothing but n times A. So note that if mod of R is less than 1, then the geometric series converges to A upon 1 minus R, that is sum of partial terms is equals to A upon 1 minus R as n tends to infinity, or it is right to say that Sn will tends to A upon 1 minus R as n tends to infinity. If mod of R is greater than equals to 1, then the geometric series diverges. Now let us start some questions here. Find the sum of following series if converges. The first part is 1 minus 1 by 2 plus 1 by 4 minus 1 by 8 plus so on to minus 1 to the power n minus 1 into 1 upon 2 to the power n minus 1 plus so on. This is a GP series with the first term as 1 and the common ratio as minus 1 by 2. Since mod of r is equals to mod of minus half is equals to half, which is less than 1, implies the given series, or we can say the given GP series, converges. And if it converges, then Sn tends to a upon 1 minus r as n tends to infinity. Therefore, sum of the series is equals to summation an and running from 1 to infinity is equals to 1 upon 1 minus of half is equals to 1 upon 3 by 2 is equals to 2 by 3. Next part, 1 upon 2 into 3 plus 1 upon 3 into 4 plus 1 upon 4 into 5 plus so on to 1 upon n plus 1 into n plus 2 plus so on to. Firstly, what we are given, that summation n running from 1 to infinity is equals to summation 1 upon n plus 1 into n plus 2. Let us simplify this term firstly. Is equals to 1 upon n plus 1 minus n plus 2. Therefore, summation n is equals to 1 to infinity an is equals to summation n running from 1 to infinity 1 upon n plus 1 minus 1 upon n plus 2. So, this series becomes 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus so on to 1 upon n plus 1 minus 1 upon n plus 2 plus so on to. So, to check if this series is convergent or divergent, we can consider its partial sum. Partial sum is a1 plus a2 plus a3 plus so on to an. And if the partial sum converges, then the series converges, and if it doesn't converges, then the series is divergent. So, an is equals to Sn is equals to 1 upon 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus so on to 1 upon n plus 1 minus 1 upon n plus 2. See, these terms are cancelling out. So, we are left with 1 by 2 minus 1 upon n plus 2. This is the value of Sn, and this converges to half as n tends to infinity. Therefore, Sn converges. If Sn converges, implies the summation an is also convergent, and its sum is half. Summation n running from 1 to infinity 6 upon 2n minus 1 into 2n plus 1. This question is similar to the B part, where we are given summation an n running from 1 to infinity is equals to summation n running from 1 to infinity 6 upon 2n minus 1 into 2n plus 1. So let us simplify this term. 6 upon 2n minus 1, 2n plus 1 is equals to 3 to 1 upon 2n minus 1 minus 1 upon 2n plus 1. Therefore, the given series n running from 1 to infinity an becomes 3 times summation n running from 1 to infinity 1 upon 2n minus 1 minus 1 upon 2n plus 1. To check if the series is convergent or divergent, we will take its partial sum. Sn is equals to a1 plus a2 plus a3 plus so on to an. This is equals to 3 common from every term, 1 upon 1 minus 1 upon 3 plus 1 upon 3 minus 1 upon 5 plus 1 upon 5 minus 1 upon 7 plus so on to 1 upon 2n minus 1 minus 1 upon 2n plus 1. Cancelling out the terms, we are left with Sn is equals to 3 times 1 minus 1 upon 2n plus 1, and this term converges to 3 as n tends to infinity. Therefore, the given series an is convergent and its sum is 3. Next part, summation n running from 1 to infinity 1 upon under root of n minus 1 upon under root of n plus 1. To check if the series is convergent or divergent, we take Sn a1 plus a2 plus on to an. So this is 1 minus 1 upon root 2 plus 1 upon root 2 minus 1 upon root 3 plus 1 upon root 3 minus 1 upon root 5 plus so on to 1 upon root n minus 1 upon root n plus 1. Cancelling out the terms, we are left with Sn is equals to 1 minus 1 upon under root of n plus 1, and this tends to 1 as n tends to infinity. Therefore, the given series an running from 1 to infinity is convergent and sum of the series is equals to 1. The next question is, find the value of b for which 1 plus e to the power b plus e to the power 2b plus e to the power 3b plus so on is equals to 9. Let us notice what we are given. We are given that sum of the series is 9 and the given series is GP with A is equals to 1 and R is equals to e to the power b. Therefore, by the convergent GP series, we know that summation of an is equals to a upon 1 minus r, which is 1 upon 1 minus e to the power b, and this is given as 9. Now, simplifying these terms, 1 is equals to 9 times 1 minus e to the power b. This becomes 1 minus e to the power b is equals to 1 by 9 and e to the power b is equals to 1 minus 1 upon 9, and this is equals to e to the power is equals to 8 by 9, and from here taking log both sides we get b is equals to log of 8 by 9. So the given series will converge if we take the value of b as log of 8 by 9. Next question. For what values of r does the infinite series converges? Find the sum of series when it converges. The series is 1 plus 2 times r plus r square plus 2 times r cube plus r to the power 4 plus 2 times r to the power 5 plus r to the power 6 plus so on to. Let us consider what we are given. We are given that summation an is equals to 1 plus 2 times r plus r square plus 2 times r cube plus r to the power 4 plus 2 r to the power 5 plus r to the power 6 and so on to. Now, taking the like terms 1 r square, r to the power 4, r to the power 6 together. So this becomes 1 plus r square, r to the power 4, r to the power 6 and so on to. And we are left with the terms 2r cube plus 2r to the power 5 plus so on to. We can take 2r common, so this becomes 1 plus r square, r to the power 4 plus r to the power 6 plus so on to, and we can see that this term and this term are similar, so this becomes 1 plus 2 times r into 1 plus r square plus r to the power 4 r to the power 6 plus so on to. Now this is my GP series with value of a as 1 and r is equals to r here. So the sum of the series for this terms is a upon 1 minus r, which becomes 1 upon 1 minus r, and this is true only if mod of r is less than 1. Therefore summation an is equals to 1 plus 2 times r into 1 upon 1 minus r, and this is valid only if mod of r is less than 1. Before going to the next question, we must make a note here that summation n running from 1 to infinity 0 is a zero sequence which is always convergent. This was the first note, and the second note say if the summation n running from 1 to infinity an converges, then an tends to 0 as n tends to infinity. This is my necessary condition for a convergent sequence, that if the sequence is going to converge, then the an term should always goes to 0 as n tends to infinity. This is a one-way result, but if we are getting an tends to 0, then we cannot say that the series is convergent always. You can take an counter example here, that summation n running from 1 to infinity 1 by n. Here the term an is equals to 1 by n. This converges to 0 as n tends to infinity, but this series 1 by n is not convergent. Based on these notes, let us do a question. Give an example of two divergent infinite series whose term by term sum converges. Let summation an is equals to 1, which is divergent, because from the above note we have considered an tends to 1 as n tends to infinity, or we can say that an does not tends to 0. Similarly, we can let another sequence bn which is minus 1, which is also divergent, because bn tends to minus 1 as n tends to infinity. But summation an plus bn is equals to summation 1 minus 1, which is a zero sequence, and this sequence is always convergent. So we have considered two divergent infinite series, but When we take term by term sum of both the divergent sequence, it converges. This is all for today. I hope you have made an understanding with these questions. Keep learning.